Hello everyone, my name is Varun and in this session, let's learn system design for distributed cache. Before we go to system design, here is a short announcement. A big shout out to Varun Vats who implemented code using Java for consistent hashing, Countmin sketch and Bloom filter. And he is our coding hero. You can also implement code for all my system design or any of the algorithm which I teach and then send the links to me and I'm going to update those links in the respective videos description. Thank you. In computation, caching is high-speed data storage system which saves the transient data so that the further request will not hit the main memory or will not compute the actual computation. And all the data will be served from the cache system. And also all the computations results will be reused using the cache. The data in the caching system usually is stored in faster access hardware like RAM. RAM provides you faster I/O operation so that you can retrieve the data which is saved in the RAM faster so that the further queries will be much faster or reduced latency. Caching is used everywhere. It is used in different layers of technology like operating system, CDN or DNS, for example. And also it is being used in many applications like, for example, websites, social networking websites, say, for example, Amazon, Google, etc. And also cache is being heavily used in games to improve the performance or latency for the read and write of the media content. So caching best practices. Before you cache something, you need to understand the validity of the data. When you know the validity of the data or when you understand how long I can save this particular data, so that's when we get high hit rate. That means that the data was cached in the cache system and we serve from the cache. Otherwise, it will cause you to cache miss. That means that the data was not found in the cache, which results in more query to the actual database or operating system. So we need to properly set the TTL, that is time to leave. As I always say in all of my videos, before designing any system, please take a couple of minutes to think about all the features or estimation you want to. If you don't know, please talk to your interviewer. So for caching system, here is the estimation. Say we want to save up to terabytes of data in the cache because we are trying to build a very big cache system, say for example for Amazon.com or even for Google.com or Gmail.com. So what is the QPS? We are expecting anywhere from 50,000 to 1 million queries per second. Okay, and also what is the latency we are expecting is almost about 1 millisecond latency to get or set or get or put. Okay, and what is the eviction policy we want to use? Let's go for LRU, and I'm going to explain something new eviction policy also. So the fifth one is the availability. So we're expecting obviously 100% availability because no one expects 50% or 80% availability. We want all of our servers to be up and running always. And obviously, I mentioned that we are going to design distributed cache system. That means that it is scalable, kind of scalable. We need to add more and more servers so that we can scale the system horizontally. So now let's learn what are the different kind of cache access patterns are there. In any application, there will be a cache and there will be a main memory. In this case, we are considering it as DB. So the first one is write through system. In this case, write through, as the name mentions, it is through. That means that whenever there is a write request comes in, it actually goes through the cache system, and then this write actually will also happen in the DB. And the acknowledgement of write successful will be sent back only when the data is completely saved in cache and also in the DB. Only that's when the acknowledgement will be sent back that the write is successful. And the second pattern is write around. In this case, as the name says, this is a write around system in which the write request will be going around the cache. That means that the write request will go to the main memory or the DB. In this case, the DB will confirm that the write is complete. In this case, the acknowledgement will be sent back. And the data will not be sent to the cache. The data will be sent to the cache or retrieved from the cache only when there is a read request and the cache miss happens for the first time, and then the cache will get that data back and then saves in the cache and then it responds. And the third one is write back. In this case, so in the write back cache system, what happens is first the write update will go to the cache and then the data will be saved first in the cache. Then the acknowledgement will be sent back immediately. And there will be one more service which will be syncing the writes which happen to the cache into the DB asynchronously. That means that the service will take care of syncing the data or updating the data which is there in the cache to the DB. So this is called as a write back cache access pattern. When we say we have to design a caching system which has less latency or it should perform get or put operation faster, what is the data structure we can use to implement the cache, the core logic of the cache? So the answer is that is hash table. So as you know, the hash table is much simpler. It works in a very beautiful fashion. So all we need is we need to have a hashing function. We need key and the value. And also we need buckets in the memory, and each bucket should be numbered like this. Say for example, we have 10 buckets over here. So the size of this bucket is 10. Okay, we have the total size is 10. Consider I want to save a value with the key tar. The value, say for example, value something, and the key is tar. What do we need to do is we have to pass this tar to a hash function, and we have to take that output. Suppose I got the output as 53. What we need to do is we have to divide the 53 with the total size of the bucket, and then we have to take the remainder. So that's the remainder is 3 in this case, because 53% of 10 we get 3. So we have to go to the third bucket in the hash table and save this key and the value both here. Say we'll be saving tar and its value over here. Okay, and then similarly, if I want to save Hulk and its value, we have to pass this Hulk to the hash function. We get the hash value called 71, and then we have to divide the 71 by 10, and we have to take the remainder. Okay, and then that is 1. We have to go to that particular bucket and save the key and its respective value, that is Hulk and its value. And suppose take some case like we want to save Ant-Man. In this case, if we pass Ant-Man to the hash function, we get 93. When I divide this, we get the remainder 3. If you go to the location, there is a collision because we have already saved a value in this particular bucket. What do we do? There are different strategies to solve that. One simple strategy is, instead of saving that value directly, we build a linked list over here. Okay, in here the value will be Thor as a key and its value, and here the value will be Ant-Man and its value. So we build the chain like that. So no matter how many collisions happen because of hashing property, we will keep on saving those key and value respectively. When the get operation happens, similarly we have to we'll take the key and then get the hashing, divide by 10, take the remainder, come to that bucket, and then check in the linked list for that particular key and value exactly for that key, and get the value and then return it back. And that's how hashing works. And I have already explained how the distributed hashing works and how hashing works in another video, which I have already posted in YouTube, and the link is available over here. And also this link I'll post in the description of this video. In that video, I have already explained how hashing works briefly, and also I have explained how we can distribute the hash in horizontal manner, or how we can scale the hash using consistent hashing. So we have to use consistent hashing to make this cache system distributed. So that is the reason I'm not going to explain how to distribute the cache or how consistent hashing works or how hashing works descriptively. Please refer to that video to understand this. So now I will directly jump to cache eviction policy. How do we evict cache? So when do we need to evict the cache? Eviction means basically deletion or removing the key and value entry from the cache memory. So why do we need to do that? Because cache is a lot expensive, because RAM is expensive. We can't keep on scaling that way. And also we know that not all the key and values pairs which are saved in the cache will be always used. So we know that, or we have to somehow figure out what is the key value pair which is been not used recently, or which is never used, and that is simply sitting in the memory idle. So we have to remove them so that we can make space for the new key value pair which the application is writing to the cache. And that is called as cache eviction policy. And we have to build an algorithm around it to evict those unused or never used key value pairs which is saved in the cache. So the best strategy is LRU. LRU stands for least recent used. There are different cache eviction policies are there, something like MRU or all of that. And the most algorithm which makes sense is LRU because it says that least recently used. That means that that particular key value pair or the cache entry was least recently used. So if it is not used, then it doesn't make sense to keep that in memory, occupying a particular bucket in the hash table. So we need to evict that so that other cache entry can be saved on that bucket. So the interesting problem is how do we implement least recently used cache? Say for example, now we have two entries saved in our hash table. So let's add one more entry. Say for example, flash. For flash, suppose we got 57 or 56. Okay, consider we got 56. So when we divided by 10, the remainder we got 6. So we have to save flash at 6th bucket. Okay, now all good. Now consider we are full of memory because we have saved even more key value pair. So now there is one more entry coming in. Say for example, Spidey, or maybe I'll write it here. So now we are trying to save this key and some value associated with it. So consider this is all full. Okay. Now we want to save this guy in somewhere. So there is no space. What do we need to do? So we need to do cache eviction. That is, we have to do LRU. So we have to somehow figure out what is the least recently used key value of the bucket so that we can delete that bucket. Okay. So there is a space available. Something like that. So we keep on deleting the least recently used buckets. So we have enough space to save this guy. So if we don't have space, anyway, there is a collision occurs because of linear probing, or for having linked list, we need memory, right? So we need to free up the memory in the hash table. So we need to do LRU. So how do we do that? So let's take a simple approach. Consider we have a list. We maintain a list in which we keep on saving the keys which are recently used. Say first we access tar, so I save tar. Then maybe I access flash, so I save flash. Say consider we have saved this guy somewhere here, so I access, so that is Spidey, and then again I access tar. Okay, so this way we can keep on saving it. The list, this particular list will keep on growing. It will be growing like crazy because we are accessing a lot of key and value pair. Because as I mentioned, we are expecting about 50K to 1 million query in the whole system. For this particular server, we might be expecting about thousands of requests, right? So this list will be growing in the rate of 1,000 keys added to this. So in this case, if I want to figure out what is the least recently used, it is a lot difficult because I can't do anything with this. I can't, even if I can do something, say if I've associated some date and time, date, a month, and year, and say for example, time and minute along with the keys, even though if what I want to do is even I have to keep on iterating with the list. So it would easily take order of n. And since the list is already growing and we have a lot of entries in the list, it will take order of n times, and that's not efficient. We need to have some sort of mechanism in which we can easily figure out in order of one that what is the least recently used cache so that we can evict that particular entry. So how do we solve this problem of figuring out what key was accessed, what key was not accessed at all, or what key was least accessed? So to do that, let's take something which we know, that is linked list, a bidirectional linked list. So to implement LRU, so we need two data structures. One is hash table and the other one is separate linked list, which is bidirectional. So what do we do is say we haven't saved any of this. Let's come in on order, first one and second one and third one. Okay. Now we want to save Thor to this particular hash table. So Thor's hash we got 53 and we know that bucket third we need to save. So ideally what we do is we'll save the value, key and value over here, right? That is Thor and its value. So now instead of doing that over here, let's keep this empty. So before we save something over here, in our bidirectional linked list, we'll have to create a first node, okay? And here we will save the key and the value, that is Thor and its value. And the address to this node will be saved over here. So I'll just mark this as 1, or maybe I'll use a different color to mark that. So mark this as 1 and I'll save that over here. So so this way we have everything intact. Say next time I want to access the value in the key Thor. What happens? Thor 53, third bucket and the address to the linked list. We go to that address, access the value and return it back. And still we are having the time complexity of order of 1. And the same thing happens for Hulk also. Say for Hulk 71, we know bucket 1. So next we will create, okay, we'll create the next node attached to that, okay. So every time when we create, consider we are saving the last known, these say start and end addresses, okay. So in this case, start is this, so that is 1, and earlier the end node also was 1 because we never had this, okay. Consider that way. So now to get that address, so using the start, we went here and then we created this node and then we link it, but make it bidirectional and then save the value Hulk here. So consider this is the address 2 and the value key Hulk and its respective value. So we know that here. Now we update the end to 2. So all good. Okay. Now anytime if you want to access this linked list, we can use the start and end addresses and we can access this data structure. Similarly, if I want to save flash 56, go to 6th bucket from, oh, I forgot to update the address here, right? So the address 2 will go here. Okay. Similarly for flash, we have to go to 6th window or bucket, and here before doing that, so now we have to access the end. Okay. So we know that we come here and then we create one more node. Okay. Consider this address is 3. We update the end to 3, and here we will save flash and we connect bidirectional. And also value of flash is saved, and then this value should be updated over here. So now all good, right? So now anytime if we get any key, we can get the value in order of 1 time. Say for example, we want to access Hulk 71 is a hash value. We go to 1 bucket 1. We know the address of the node, so we go directly to this particular node, and then we get the value for associated with Hulk. We just return it back. So everything is still working the way it was supposed to work. Now, how this particular bidirectional linked list will help us to figure out LRU. So that's the trickiest part. So if you see over here, this linked list represents the order at which these keys were accessed. Say we accessed Thor first, second Hulk, and flash third. So at any point of the time, okay, if I want to know that what was accessed very early or which was accessed recently. So we know that flash was accessed recently and Thor was accessed very first. If I want to clear something off, I can easily clear this off because this was accessed first and this was accessed very recently. So now I can easily remove, because if this guy was accessed recently, this guy would have been in the first of the list. I mean, from this end, right, to the right side of the linked list. Because it is in the left side, we know that this was the very first element which was accessed. And we can easily clear that off. Okay, so that way somehow this representation is telling us the order at which these keys were accessed. So anytime we can figure out what was recently accessed, what was accessed, what was the older key which was accessed. So okay, now consider what happens. The same keys are accessed again and again. So consider Hulk was accessed again. What happens now? Hulk 71, we go to bucket 1. So we know the address over here. We go to 2. So now since this is accessed, for now this is the latest record which was accessed. What we need to do is we'll have to remove this guy from here. So in linked list, removal is order of 1 because it's bidirectional. All we need to do is we have to remove this Hulk here, okay, and then link these two guys. So it is still bidirectional linked list, and append that guy which we remove to the first of linked list. Okay, how do we need the first? Because we know the end of the linked list from this entry here, right? So 3, link it over here, and then say, for example, we got the address, same address, say 2, and then we update the value, same thing, right? It's Hulk, and its value over here. And now the end value is 2, so let's update that also. So okay, now still all good. Now this representation is again telling us the order at which the keys or the data from the cache was accessed. Now still I know that this was accessed very first, and this is the very latest record which we accessed. So now if I want to clear that off, I can easily clear from the left side of the linked list. I can clear this, I can clear this, I can retain this. All right, if I have a bigger chain, I can keep on clearing it from the left side or the starting end of the linked list. That way, we know the order at which the keys are accessed. Anytime when the key is accessed, we can delete the node in the double linked list in order of 1, and we can append to the right side of the bidirectional linked list in order of 1. So everything is working still in constant time. The only thing is the linked list is taking extra memory, and that is fine because we have to have LRU eviction policy. So this way, we know that what are the keys we can delete, what are the keys which are least accessed. So LRU is the most used cache eviction policy because of its simplicity and simple to implement. But the problem with that is it just keeps record of which was the least accessed or which was the most recently accessed key and value pair, but it doesn't anyway count the frequency of access or what key was accessed how many times. For that, there are other implementations which uses Countmin sketch. I have already made a video on Countmin sketch on how we can calculate the frequency of any given key value pair which is coming in much faster frequency efficiently. Please go and watch that particular video to understand how we can actually use Countmin sketch to calculate the frequency with less memory, with less accuracy. So now, how do we design the internals of our caching system? So we know we have hash table, and we know we are using RAM, we know we have LRU cache eviction policy and everything. But still, we need to have a service which accepts the requests like get, put, delete requests, and then we have to update the data into hash table, and then we have to read the data if there is a get request, and if there is a delete request, we need to delete that. Since we know that we are using RAM, even though it is faster, it is kind of blocking call, right? So we need to have an efficient way of serving these requests. One way we can do is we can spawn n number of threads as and when we get the request, or we can have a bigger thread pool which can handle that. And these things will not scale and it will cause a lot of problems. The easiest way we can handle is event-driven logic, in which, say for example, and here we will have an event queue in which any request like get, put, or delete request will first be placed into the event queue. And then we will have a event loop which is running, which is a single threaded operation, which will be running indefinitely. And we have a thread pool here, which just takes care of the IO operation to the RAM. What happens when a get request or put request is requested, that particular request will be placed into the event queue. The event loop, on the other hand, will be keep on reading the queue and handing over the request to the threads which are free in the thread pool. And once it handovers to the thread, it will come back and then which reads the next event. That way, the event loop is never blocked. The threads will do their own work. The thread which receives the request will do the IO operation and gets the data. And also, um, the the event loop would have given the callback function, and that particular thread will execute the callback, or it transfers the data to event. Sorry, it will execute the callback, and the response will be sent back to the request, either through the event loop or some other mechanism. And this is how we can handle the request more efficiently. So now, how do we make our caching system fault tolerant or persistent? As we know, all of our cache table and the data is saved in the RAM for faster access or faster IO operation. What if our system for some reason restarts or something happens and all the data in the RAM is lost? That means that our cache system is not persistent. So to make it persistent, we have to do something, okay? Uh, Somehow we can retrieve back all of that data. So there are two approaches to that. So first one is regular interval snapshot. So the name snapshot indicates that we take a picture at a certain state and keep all of the data saved in somewhere, something like hard disk. So what we do is, so there is a read and write operation happening here on the hash table. So we'll have a service running in the background, that is asynchronous service running in the background. So it will take a frozen copy of the hash table and place into the dump file, and this will be saved in the hard disk. Okay, that's one way to keep our snapshots in the dump file regularly or a particular interval of the time, and that's how the Redis also does. So the second way we can do is by log construction, or sorry, by log reconstruction. So in this case, what we do is, so instead of having a asynchronous service to which takes a snapshot of the hash table and save it somewhere, what we can have is the service which retrieves the hash table, the key value data from the hash table, will keep on doing its job, and also it will be logging the entry or the operation into a log file. So what happens is, say read, write, say write key and value, read key and value, say delete key and value, something like this. It will be keep on entering all the operation and the key and the value data into a log file, which is there in hard disk. So since it can't be part of the synchronous request going on, make this as a sync call, which will be keep on updating into the log file, or we'll have some kind of buffer in here, a queue or something, which enters the log so that the performance of the read and write will not be affected. And in the queue, we'll have one more service which reads from the queue and then updates into the log file. So why do we need this log file? As I already said, log reconstruction. If we have each and every operation we performed on this particular hash table, even though if our machine goes down and it restarts and come back, if we have access to this log file, we can reconstruct the whole data or the final copy of the data which was supposed to be there in the hash table by executing each and every instruction in the time sorted order. That way we can still recreate the hash table, because we know the operation, we have the key, we have the value. All we need is we have to recreate the whole scenario in the flash of time, and then we fill the data into hash table. So with these two strategies, we can think that we made our cache system persistent or fault tolerant. So now we learned how to make our system fault tolerant or persistent. Now let's learn how do we make our system available or 100% available. Okay, so consider in our node we have, or in our cluster we have two nodes, that is node 1 or server 1 or server 2, and both have its own cache table Say we are using consistent hashing. Consider this is handling some key and value, and this is handling some key and value. So this all is good. So the problem with this strategy is, what if this server goes down? Okay. Now, if this server is not available, all the requests which are coming to this cache will have cache miss, or it won't even respond. So what happens is all the requests which are coming to this, supposed to go to the server, will be going to the DB, and hence the read and writes on the DB will increase. So we have to make something to avoid this kind of problems when the server goes down. So what we can do is we can have a replica of this server. Say, for example, say we'll say as a replication factor 2. That means that we'll have to replicate every data into 2 copies. Say we'll have one more server which acts as a mirror image. Okay. Okay, that is one complement or something. Okay. For this also we'll have one more server. So whatever the data which this guy has, the same data will this guy also have. Now the advantages of this setup is, now the load is also reduced because the request which is going to the server 1 can also be shared with the server 1 complement, or the copy of server 1. That way, the read requests are kind of distributed. We get less latency, and the performance is a lot better. But the problem is we have to keep syncing the updates from which happens between these two servers. There is a little latency. Even in case of write or read, there is a latency for syncing between the data between these two servers. The same happens here also. When we have network between these two machines, there can be inconsistency when we read the data. So that's the problem with this setup. So how do we solve this? What we can actually do is, instead of having the copy of the server, which can be used for read and write both operation, what we can simply do is, instead of making the server as a mirror image, let's make that server as the slave. Simply, it has a slave 1 machine. This is slave 2 machine. So in this case also, the data updates and everything will be going here. The second server's data updates, writes and deletions all will be updated. Basically, the data is synced between this, but the reads and writes always happens on the master servers, that is on these two servers, and the requests will never be touching the slave server until this masters goes down. Okay, so this is one way to solve the problem. Yes, that's the end of system design for distributed caching system. Please go through the videos which I mentioned in between the explanation. One is consistent hashing, that exactly tells you how to distribute the cache system, okay? And the second one is Countmin sketch, which exactly tells you how you can actually calculate or keep track of the frequency of access for any given key. Based on that, also you can devise an algorithm which can predict which key to be dropped or which key to be evicted, okay? I have provided those links in the description. Please make sure you go through those videos, and those are really good videos. So task for this video is, I know it is a lot difficult to implement the whole caching system. Instead, at least try to implement the hash table or the whole hash map implementation. And also, if possible, try to implement consistent hashing. And please provide the links of your code, which is hosted in GitHub or anywhere. And I'm going to update those links on this video's description. If you like this video, please subscribe, tell your friends to subscribe, and also like, share, and comment. Thank you.